This is section 11.2. It's not going to be quite as dry as 11.1, but there is still quite a few definitions of things that we're going to go over. So again, if you would prefer to read section 11.2 in your text, you're welcome to do that or follow along in 11.2, subgraphs, complements, and graph isomorphisms. Let's take a look at a subgraph to begin with. And a subgraph, H, is called a subgraph of G. So G is my initial graph, and you can see I've given you an example here of what maybe a graph G would look like. And the subgraph H is an example where all of the vertices and edges that are within H are in G. And what I mean by that is for my subgraph H, I can't just make up a new vertex. Also, any of the edges contained in H are also contained in G, assuming all edges are incident to the vertices contained in the graph, which essentially means I can't make a floating edge that is in the original graph but doesn't connect to a vertex. So let's take a look mathematically what this means. This is saying the set of vertices is a subset of the set of vertices of G, and the set of edges is a subset of the set of edges, and implies that they are incident. Again, let me show you some examples and some non-examples. So here's my original graph G. Notice this is an example of a subgraph. I've got A, B, they're connected with an edge. The same two vertices and edge are contained in my original graph. Here's another subgraph. Notice I've used all of the vertices, but I left out this guy, and that's okay. Another, I've used only A, B, D, and that's okay too. Now, what I can't do is, here is a non-example. So why is this a non-example? Because as you can see, even though I've used A, B, C, D in the proper places, I've added this edge. I can't add edge BC because it wasn't contained in my original graph, so therefore that is an example of not a subgraph. Also, I can't use this because this guy isn't connected to a vertex. So I would have to include C, and then it would really just be the same graph over again. But I can't just drop the vertex. If I drop the vertex, I would have to get rid of that edge as well. A particular kind of subgraph is called a spanning subgraph, and essentially what that means, or that tells us, is that the vertices must be the same. So here, as you can see, I've got one, I'm just going to number these so we can specify which one is which, 2, 3 examples of spanning subgraphs, and what they have in common is that each of the subgraphs include all of the vertices from my original graph my original graph G. So each H, which is each subgraph, all have the same exact vertices as my original graph. So for 1, I've essentially included everything except I decided not to include the loop on D or edge DC. For 2, I said, here's the vertices, I'm not going to connect anything. And for 3, I said, let's take out AB and AD and include everything else. And again, it's okay to do that as long as I include all of the vertices. Another specific type of subgraph is called an induced subgraph. And this occurs when I remove a vertex and any of the edges that were connected to that vertex. So again, you can see the mathematical notation. I'm taking G, which is my original graph. I'm subtracting some vertex, and that's going to give me some smaller set of edges as well, since anything that was connected to the vertex that I'm removing must also be removed. So let's take a look at 2 examples. So here's my original graph G. My induced subgraph by removing C. So here's C. If you'll notice, there is a BC and a DC, and you'll notice in my induced subgraph BC and DC are gone, as well as C. So C would have been out here. It's gone. I took away anything that was connected to C as well. One more example, if I remove D, so here's D. D, I would have to take away AD, DB, DC, and the loop on D. So I'm left only with A to B to C. Let's shift away from subgraphs for a moment and revisit a complete graph. We talked about what a complete graph was in section 11.1, and we essentially said it's an undirected graph that's loop-free where every vertex is connected to every other vertex. And essentially that's what it is. I want you to note the way that we're going to denote this. So K sub n, if it's K1, that's a complete graph with one vertex, whereas K3 is a complete graph with 3 vertices, etc. The important thing here is first that it's undirected, and also that each vertex is connected directly to each other vertex. So I've given you the examples up through K6, and I do want to point out that I've given you 2 examples for K4, and that is because this is the one you'll see quite often for K4, but if we're looking for a planar graph, which we haven't talked about planar yet, but a planar graph essentially is where I'm not going to have any edges that cross over one another. So this is another example of K4 where everything is connected to everything else, but you'll notice that instead of crossing over that other edge in the center of my figure, I've taken the long way around so that I no longer have anything that crosses. But these are some examples up through K6 of complete graphs. Building off of those complete graphs, so for instance, here's an example of K4. This is the planar version of K4. If I want to look at the complement of a graph, G. So here's my graph G, and if you'll notice, I have A, B, C, and D that I have in my original graph, and I'm only using a few of the edges of the complete graph. The complement is essentially using any edge that's not in the original graph. So notice I'm still using A, B, C, D that were in the original complete graph, but my complement is going to include this AB that I didn't use, this BD that I didn't use, and then from A to D, A to C, B to C that I didn't use in graph G. So anything that I didn't use in graph G, I have to use in the complement of G. And again, note the way that we're denoting that is just a G with a line above it, meaning the complement of G. My question, going back to complete graphs, is can I do some generalization? Obviously, we love generalization in mathematics. So I'm saying, yes, I've been nice enough to give you the complete graphs through K7. And I was nice enough to tell you how many edges I drew by keeping track as I drew them. My question is, what if I wanted K100, or the complete graph where I had 100 vertices? How many edges would I have? Well, obviously, that would be a real pain in the rear to first of all draw 100 vertices, and then to count as I'm drawing them how many edges I needed to connect everything. So let's generalize. I've given you some hints, which is of course some examples through K7. Also that it seems each vertex contains n-1 edges, so in K3 this guy has 2 edges, 2 edges, 2 edges, but I end up at 3. This guy has 3 edges, 3 edges, 3 edges, 3 edges, but I end up at 6. How can I generalize this? Try that on your own if you're up to the challenge, and when you're ready, press play to see if you came up with it. Hopefully you gave that one a shot without just moving on to the next part of the video, but I know if it were me, I probably would have just moved on to the next part of the video. But you may have come up with the fact that the number of edges of a complete graph, Kn, where n of course is the number of vertices, can be found by taking n times n minus 1 divided by 2. In other words, we can take n choose 2. So let's double check that. If you'll recall, on the last page I told you that K6 was equal to 15 edges. So let's just double check that with our little formula here. Our formula says I can take 6, which is n, times 6 minus 1, which is 5, divided by 2. That's 30 divided by 2. That's 15. It works out. You can check as many as you'd like, or you can take my word for it. Completely up to you. Now, this brings us to the first theorem of graph theory. The first theorem of graph theory says if we have a graph with n vertices, and notice this is not specifying a complete graph, this is just any graph with n vertices, then the sum of the degree of all of the vertices is equal to 2 times the number of edges. Now, hopefully, the concept of that is pretty straightforward. Let's think about that for a moment. Here's a graph I'm just obviously making up as we go. A, B, C, D. When I draw an edge, what happens? Well, I've just added a degree of 1 to D and a degree of 1 to B. Let's add another edge. B to C. Well, I've just added a degree of 1 to B and a degree of 1 to C. So every time I draw in an edge, I'm actually adding 2 degrees. And that's really all this is saying, except it's going backwards. It's saying if I take all the sum of the degrees, then it's the same as if I took each edge times 2. So here I have a degree of 1, 2, 3, 4, 5, 6. And how many edges do I have? I have 1, 2, 3 that I drew in. So essentially I'm saying if I took 2 times E, that would be 2 times 3, or 6, which is of course the degree. Now, that's just a way for me to explain it to you so that it makes sense. Obviously, there can be proved through induction or recursion. I'm going to leave that proof to you. I would suggest that you try it on your own, and when you're ready you can obviously Google that proof as well. But I would suggest that you look at that proof. Here's another generalization question, but obviously I'm not asking you to try it on your own. We're going to work through it together. This question says how many graphs exist with n vertices where the vertices are labeled. So here we're looking specifically at labeled vertices, and essentially what that means is that, I'm going to use my 3 vertices as an example for a moment, that these are all different graphs, and they're different specifically because I've labeled the vertices. So if I were doing this same thing with unlabeled vertices, then this first graph would really be the same graph rotated for this guy or for this guy. But because we're dealing with labeled graphs, they count as 3 different ones. So let's take a look at how we can generalize. For one vertex, there's just one graph. For 2 vertices, there is the unconnected graph, AB, and then there's the connected graph, AB, so there's 2. Now, for 3 vertices, I've got the unconnected graph. I have 3 versions of a graph with just one edge. I have 3 versions of a graph with 2 edges, and then of course I have the one graph where all 3 edges are represented. So let's put together what we know about the complete graph. So we talked before about the complete graph would be 3 choose 2 total different edges that I could draw in, which would be 3 times 2 divided by 2, or 3 total edges. And we can see that here, that there are 3 total edges that I could draw in. Essentially what I'm doing is I'm choosing how many of those 3 edges to draw in. So I'm saying here's 3 choose 0, because there are 3 edges I could have drawn. I chose not to draw any. 3 choose 1, and again that's 3 different versions. I chose one edge, I chose a different one edge, I chose the last different one edge, and then I looked at 2 edges, a different 2 edges, and the last different 2 edges. And then of course all 3. So what I can do to generalize is say for 3, I noticed 3 choose 1, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. That all adds up to 2 to the n, because this was 2 to the third, which was 8 total different graphs for labeled. And so essentially, instead of 2 to the 3, I'm going to say 2 to the n choose 2. So again, where did n choose 2 come from? N choose 2 gives me the number of edges that I have to choose from. So it might look funny looking at this to begin with, but if we know this is the number of edges, and essentially I'm saying 2 to that power, it makes perfect sense. For 2 vertices, there's just one edge that I can draw in. So that's 2 to the first, which is 2. So if I looked at 4, the complete graph of 4, K4 is 4 choose 2 total edges that I could draw. That's 4 times 3 divided by 2, which is 6. So this would be 2 to the 6th would be the number of different graphs that exist with labeled vertices for a K4. I specified last time that we were talking specifically about labeled vertices. What if I took away that restriction and said they're not labeled? Well, we talked before about the fact that this guy is a distinct graph. These 3 are really all one type of graph. So if you'll notice, yes, I just copied and pasted, but these 2 would not count as different graphs because I could just, turn them around and make them the same graph. So I could rotate this guy in this direction and end up with this guy, etc. So I've got 1, 2, these 3, again, all the same graph essentially. Notice not labeled vertices. This guy I crossed out and this guy I crossed out because there's still a graph with 3 vertices where only 2 of them are connected. And then, of course, my complete graph for K3. Now, if you'll notice, I got 1, 2, and 4. So it's a little bit different. It's a little bit more difficult. We're going to have to use Pauli's theorem. But we can see that all the labeled graphs contain 1 edge are now considered the same unlabeled graph. All that contain 2 edges are the same unlabeled graph, etc. So my question is, how are we going to now generalize this? This brings us to the concept of an isomorphism. And we're not going to spend a ton of time on the mathy definition of an isomorphism. You may have already studied this in abstract algebra, or you may not have yet. I want to focus on the more practical definition than the mathy definition. So I have provided you with the mathy definition, but essentially what we're saying for an isomorphism is we're saying 2 graphs are isomorphic if they have the exact same structural properties, which means they have the same number of vertices, they have the same number of edges, and the edges contain or connect are incident to the same vertices. So let's look at just a practical example instead of getting caught up in the mathematical lingo of the definition. So my question is, are G and H isomorphic? So notice here I've given you 2 different graphs, one G with vertices 1, 2, 3, 4, one H with vertices A, B, C, D. They don't look the same, but my question is, could I take H and relabel? So could I relabel these guys to come up with essentially the same vertex and edge sets? So graph G has vertices 1, 2, 3, 4. Graph H has vertices A, B, C, D. The edges contained in graph G go from 1 to 2. That's this guy. And from 3 to 4. So my question is, can I just relabel H and say, let's call this 1 and let's call this 2. So far, so good. I have edge 1, 2, and if I relabel this 3 and relabel this 4, then I have an edge 3, 4, and I essentially have done it. Now, if you'll notice, this is also a graph H, which still works because I have edge 1, 2 and edge 3, 4. It looks a little bit different than the one I created up here, but essentially because I can make them match up, I can assign that, and let's just focus on this one I have drawn down here, that f1, which means my function of 1, is a, which means my original a is now f of 1. f2 is d. So my original d came from me relabeling it as 2. f3 is b. So my original b is now f3, and f4 is c. So essentially it's taking this and saying, how did I manipulate that? Which means 1 and 2 is now AD, and 3 and 4 is now BC. Let's look back at the mathy definition now that we've looked at an example and see if we can make sense of that. Essentially, we're saying there's a function that is 1 to 1, which is why it's bijective, 1 to 1, that maps each vertex from one graph to exactly one vertex in the second graph. And that's this guy, 1 to 1. In addition, if there is an edge in the first graph, then there is a corresponding edge in the second graph. That's this one. Here's a question for you to try. Is G isomorphic to H? Tell why or why not. If it is isomorphic, provide the mapping. Tell me which vertex would become which other vertex, which edge represents which other edge. When you're ready, press play to see how you did. Hopefully you were able to tell fairly quickly that this one wasn't going to work. And really one way to look at that is this guy has a degree of 2 at each and every vertex, and this one does not. So there was no way that I was going to be able to relabel graph H to make it match up with graph G, because my degree structure is not the same for each of the two graphs. Here's a very easy way, or a quicker way, to determine, this is the graph isomorphism theorem, 3 steps that I could go through to determine whether or not two graphs could be isomorphic. So notice I'm looking at the exact same example. We've already determined, no, these are not going to be isomorphic. The first thing I would check is that both G and H have the same number of edges and the same number of vertices. So here I've got 4 vertices, I've got 4 edges. Here I have 4 vertices and I have 4 edges. So based on this theorem, it's still a possibility. The second thing I would check is the degree sequence structure. And this is something you may have not seen before. Essentially, I'm saying, in my 4 vertices, how many have a degree of 0? 0. How many have a degree of 1? 0. How many vertices have a degree of 2? Well, 1, 2, 3, 4. And that's all. So zeros from there on out. If I look at H, how many have a degree of 0? 0. How many have a degree of 1? 1 of them. How many have a degree of 2? 2 of them. How many have a degree of 3? 1 of them, and then zeros from there on out. And as you can see, because these two things are not the same, these are not going to be isomorphic. Now, if you make it through steps 1 and 2 and you're still in yeses, then you would look at a cycle structure. So again, we're looking at a cycle 1, 2, 3, 4, whereas this is a 3 cycle, and again, they're not isomorphic. One last question for you to try. Use that graph isomorphism theorem to go through the checklist to see if these are, in fact, two graphs that are isomorphic. If they are, provide the mapping. If they're not, tell me why not, using one of those things that we talked about in the graph isomorphism theorem. When you're ready, press play to see how you did. So 1, G and H both have 6 vertices and 9 edges, so they could be isomorphic, but again, looking at the degree sequence structure, it fails. I'm not even going to check 3, because if it fails 2, why move on? It's very clear to me that these are not isomorphic because the degree structure is not the same.